and welcome yet again to the eLearn program brought to you by the Division of Education, Innovation and Energy. My name is Mr. Chet, and I'll be continuing on a part of organic chemistry. We would have started this part, and I pray that through this lesson that you will learn and it would be helpful for you in the long run. All right, so let's press ahead. So the topic we're going to be looking at today is naming and drawing alcohols and alkanoic acids. Last class, we would have learned how to draw and name alkenes. All right, so we would have looked at the isomers of alkenes. We'd have learned how to draw them. We would have learned the rules of drawing them, and we would have done some practice problems. Today, we're going to be doing something similar with alcohols and alkanoic acids. All right, so let's look at some of the objectives that we have for today. So one, we are going to, at the end of this lesson, you should be able to draw and name isomers of alcohols, isomers of the alcohol homologous series. And you are also going to learn how to draw and name alkanoic acids. And lastly, we are going to practice some CSEC type questions applying what we have learned thus far. So, alcohols. What are alcohols? Alcohols or alkanols have a hydroxyl group, OH, as their functional group. The general formula of an alcohol is CnH2n plus 1 OH, and alcohols, as we would have learned in the previous videos before, alcohols are named by using the prefix indicating the number of carbon atoms in the molecule plus the ending of anol. So an example we have CH3OH. This compound has one carbon, and we know one carbon means meth. Therefore, the name that we're going to come up with is methanol. Structural isomerism in alcohols. So let's look at some of the structural isomerism that we would have in alcohols, if there are any. All right, but I'm sure there are. So what we're going to do, we're going to draw out the structural formulas for all isomers that can be formed by the following alcohols. So we have CH3OH, C2H5OH, C3H07, and we have C4H9. And we also have C5H11OH. So let's take a look at each of them. So we're going to look at the first one. All right, can we have structural isomerism from this particular one? So let's just bring this over here and let's begin. All right, so we have an alcohol that contains one carbon. All right, and we have 3 hydrogens, and we have an OH group that is bonded to it. So we draw this here, and we will ask our question, is there any other way that I can draw this particular alcohol? The answer is no. All right, there is no other way because the OH group is going to be still connected to the same carbon. So we're going to erase this one here, and let's look at the next one, and let's see if we can have a isomer forming from the second one. So the second alcohol we have contains 2 carbons. So we draw them out, 2 carbons. And we know alcohols have an OH group. So we put the OH group, and there are 5 hydrogens. So we're going to put them in 1, 2, 3, 4, and 5. So we place them, the hydrogens in, and we observe. Is there possible to have an isomer? All right, if we can recap what an isomer is basically a compound that has the same molecular formula but a different structure. All right, so we are asking if this alcohol that contains 2 carbons can form an isomer. Can we change it up? The answer to that is no. All right, reason being, and we're going to get that more when we get down into naming it as well. All right, now if I place the OH and I switch it and I put it on the next side, would that make it different? No. And if you would have learned from the videos and them that we had before, we would know that when you place a functional group, you need to make sure you give a functional group the lowest possible number. So the carbon that the functional group is going to be on is always going to be carbon number 1. So in this case, we are not going to find any structural isomers with a alcohol that contains 2 carbons. All right, let's look at the next one, the third one. Let's move ahead. So let's look at it. So we have 3 carbons, 1, 2, 3. And of course, we need to have an OH group connected to here. And we need to find out, is it possible for us to have an isomer coming from this particular alcohol? The answer for that would be yes. All right. Now, if I move the alcohol group that I have here presently, and I shift it to the adjacent carbon, which is this carbon here, we are going to result in having a different structure. Okay. So let's take a look. So if I'm going to move, I will have 3. Let's erase this to make some space. Enjoy it enough. So we have 3 carbons, 1, 2, 3. All right. And we said we are going to shift the OH group, and we're going to put the OH group right here, which is the carbon in the middle of the 2 carbons. And each of these carbons are going to have the hydrogens connected. So there we have it. As we can observe, we have a different structure. All right. So where this is concerned, can an alcohol with 3 carbons have an isomer? Yes. Is there any other isomer that can be formed from an alcohol with 3 carbons? No. There are no more isomers. There are no more isomers that can be formed from this carbon from this alcohol that has 3 carbons. Okay? All right. If we try our best and we can go down, we are going to find out that the alcohol containing 3 carbons can only form 2 isomers. All right, so let's go down. Let's look at the next one. So we're going to add 1 in, and we're going to look at the next isomer, or the next alcohol compound that has how many carbon atoms? 4. All right. Just erase these here, then we are going to move. So we're going to look at the one that has 4 carbons. So how are we going to draw this? We place out our 4 carbons. 1, 2, 3, 4. So we have 4 carbons placed out. All right. And we know that there must be an OH group present. So we begin by drawing in this way, and we make sure that our carbons have all 4 bonds facilitating them. So we're putting our hydrogen, and we are going to find out how many isomers we are going to get from the 4 carbon alcohol. So a 4 carbon alcohol, this is the first isomer that we have. So we are going to draw the second isomer, and the second isomer, of course, is going to have the 4 carbons present. And this is a very important note that I want you all to note here. All right. So when drawing your isomers, one of the first steps you should take before drawing your isomer is to shift the functional groups. As you shift the functional group along the carbon chain, you can, and finding different variations, you would be able to draw a different isomer. You begin by doing this first, and following from there, then when you have exhausted all the possible isomers that can be formed, you then will seek or look into doing branch chains. All right? And we are going to explain or give an example where that is concerned. All right, so where this is concerned, we are going to be moving the OH group, and we're going to put it on the adjacent carbon. So we're going to put it on this carbon right here. All right, so we're going to observe it on this side. So we're going to put the OH group here. So it means that we're going to have hydrogens being placed on all the other areas of the carbons, connected to the carbons. All right, so we have a different isomer from here. All right, so, okay, let's see if we move the carbon down again. If we move the carbon, the functional group, if we move that functional group from that adjacent carbon, that second carbon we placed it at, and we add it on the adjacent carbon, what is going to happen? Let's check and see. Are we going to have the same compound? I can hear some of you all saying, yes, sir, we are going to have the same compound. All right, so I'm just erasing this OH group, and instead I'm going to put it on this carbon that we have here, which is OH, and place the hydrogen here. All right, now in placing that OH group, that functional group there, is it different than the one we had before? You may observe, you may say, some of you may say, yes, sir, it's on the third carbon. But please note that when drawing your isomers, we want our functional group to have the lowest possible number. So instead, we are going to begin numbering from the opposite side. So instead, we're going to be numbering here 1, 2. So here it's going to still be the second carbon, whereas on the last side, we had 1, 2 being here. It's going to be the second carbon. So it's actually the same compound that we had initially in the example before. So it's the same carbon. So this is not an isomer, all right? It's not a different isomer. It is exactly identical to the one that was placed before. So it's the same, all right? So if it's the same, that means we have exhausted all our possible options of having isomers with the functional group alternating on the carbons, all right? So next step is to do branching. So let's begin branching. So we're going to move. So I'm going to go back to this compound here, and we are going to move this carbon. Okay? So I'm going to draw another one right in the corner here. So if I remove, I'm going to have 1, 2, 3 carbons remaining here. 1, 2, 3 with an OH group on it. And I'm going to move this group that I just named, and I'm going to put it on the adjacent carbon. I'm not going to put it back on the same carbon that it was bonded to. I'm going to put it on the adjacent carbon. And I'm going to just represent it by CH3, which is in the condensed formula, which we know CH3 is actually meaning a carbon that contains 3 hydrogens bonded to it. All right? So that's what this means. All right? So I'm just going to place it in this form. And we are going to place it like this, and we have our hydrogens. So do we have something different? Yes, we do. All right? We do have another isomer. Okay? So now, can there be another isomer that comes from this? Let's check it out. All right? Now, the next isomer that some may say, all right, sir, let's move another group. All right, let's move another carbon and put it in. So you can explore all your options, all right? But just for time's sake, I am going to just take this second compound, and instead I'm going to move this carbon here, and I'm going to form another isomer. So I'm going to have 3 carbons, 1, 2, 3, okay? And I'm going to move that carbon to the adjacent carbon, which I'm going to put here, CH3. And I'm going to have my OH connected to that carbon. All right. So let's see if that's something different. Yes, indeed it's something different. All right. If we look at, this was the first one. This is the second one. This is the third one that we draw. Now this is the fourth isomer that we have drawn. All right. Looking at the third isomer, we are seeing that the branch is located here. Let's see if I can get a different color here. The branch is located here. All right. As well as on the fourth one, the branch is located here. However, the difference that we have is that the OH group on this one is found on the first carbon, which is carbon number 1. And this, the OH group, is found on the second carbon. This one here is going to be 1, or vice versa. You could have called here 1 instead, all right, as well. Okay, so they are not the same compound. All right, so these just are examples. Now we have C5 which follow, but we are not going to go into that. You can practice that and see how much isomers you can get. But what makes these things easier, what makes the isomers easier, and you understanding whether or not your isomers are correct, is understanding how to name them. And understanding how to name them is what gets us, give us the understanding that our isomers are actually different. All right, it just kind of helps us to put some checks and balances to ensure that the isomers that we have are really isomers. So let's press ahead. So we're gonna, what have we learned so far? We learned that alcohols with 3 or more carbon atoms show structural isomerism, resulting from a change in position of the hydroxyl group. As I said, that's the first step we're going to take, and as well as branching of the molecule. All right, so let's look at these here, the isomers that we would have here for C4H9OH, and since it's 4 carbons, we're going to call it, since 4 is bute, we're going to call it butanol. So from butanol, how many isomers can we have? We found that we can have 4 isomers. 4 isomers from butanol. All right. What are the names of these isomers? They are not the same, so they're going to be named differently. The molecular formula, C4H9OH, would be the same, but the names are going to be different. So the first one we call it butan-1-ol. The second we call it butan-2-ol. The third we call it 2-methyl-propan-1-ol. And the fourth we call it 2-methyl-propan-2-ol. All right? So the question is, sir, how did you get to know these names? How am I going to be able to name these compounds? So let's see. All right, so I'm going to show you how to do them now. So naming isomers of alcohols. To name unbranched isomers of alcohols, one of the first things we need to do is indicate the carbon chain based on the number of carbon atoms using the prefix. Of course, we know this one. Based on the number of carbons we have in the compound, you can use, based on the number of carbon compounds within the compound, we use a prefix, and that prefix could either be met, et, prop, bute, pent, etc., etc. All right, and we are going to get that name. So that's the first one. The second one says number the carbon atoms in the continuous chain of the carbon atoms from the end closest to the OH group. All right, we're going to demonstrate that just now. And the third one, we said indicate the position of the functional group using the number of the carbon atom it is bonded to. So let's take an example. So we have a name here, butan-1-ol. So we said that first thing we need to know how many carbons we have. So the number of carbons we have is 1, 2, 3, 4. So we have 4 carbons in it. So we know that we have bute. So that's the first part. That's where we get bute. Okay? Now it says number the carbon atoms in the continuous chain of carbon atoms from the end closest to the OH group. So we have the OH group here. So we are going to name them. We are going to number the carbons from this end. So we're going to put 1, 2, 3, 4. There's a reason why we did this. Now next we said indicate the position of the functional group using the number of the carbon atom it's bonded to. What carbon atom is this OH group bonded to? It's bonded to the first carbon. All right. So afterwards, this is how we get the name butan-1-ol. So bute, because it's 4 carbons we have in present, so we call it bute. Since it's an alcohol, we know that we have to add anol to it. Now we need to indicate, all right, we need to indicate the position of the OH group. So to indicate the position of the OH group, I use the number that it's bonded to. So instead we're going to call it butan and OL, which is 1-ol. Or in simpler terms, you can call it 1-butanol. All right. Most students prefer to use that one because it can alleviate you making some errors. Sometimes students would say but 1 anol. All right. And you would understand what they mean by it, but it's not the standard, right? So 1-butanol is a very good way of writing your isomer. All right, let's look at the next one now. So we have a next example here. We have butan-2-ol. So butan-2-ol, how was the name derived? The same steps that we would have learned. All right, so there's 4 carbons within the molecule. 1, 2, 3, 4. So we know that we have but. Okay, then we look at the OH group. So we're going to number the carbons on the continuous chain of atoms. We're going to name on the end. We're going to start beginning numbering the carbon on the end closest to the OH group. So I have a carbon here and I have a carbon here, but the one closest is this carbon. So I'm going to call this carbon 1, then carbon 2, then we have 3, then we have 4. So we do have 4 carbons. All right. And lastly, we indicate the position of the functional group. So the functional group, which is the OH group, is found on the second carbon. Hence, we say that it is 2-butanol. All right. So always remember when we are naming, we separate the numbers by the hyphen, all right, from the name. So that's how we normally do it. These are the standards that we will follow. All right, so let's press ahead. So we're looking at naming the isomers of alcohols. All right, so let's look at the branch isomers then. The branch isomers are named by 1, number the carbon atoms in the longest continuous chain of the carbon atoms from the end closest to the OH group. Indicate the position of the functional group using the number of the carbon atoms it is bonded to, just as we did in the first one, and a name and number the location of the side chain or the branch. So let's look at that. So this is our next example here. How did we derive these names? Using this particular step. So the first step was to number, all right, the longest continuous chain. And in addition to that, we know that when we are numbering, we need to begin by numbering the carbon. When we are numbering, we need to begin by numbering the carbon that is closest to the functional group. So this is the functional group here, and we want to find the longest chain. Let's go. So we're going to go 1, 2, 3. So we have the longest chain being here. We could have gone 1, 2, 3 otherwise, but this is the longest chain that we are looking at here now. So next, we say you have to indicate the position of the functional group. The functional group is found on the first carbon. 1, 2, 3. So it's found on the first carbon. And of course, lastly, this is where we're going to get the name 1-propanol. All right, because the OH group is found on the first carbon. And then we are going to add the branch. So the branch is located here. So what we will call this branch, since it has 1 carbon, and we are looking at the rules we have learned before, branches with 1 carbon, we refer to them as being methyl, all right, or methyl. So since we have methyl, and we now would indicate so we name and the number the location of the side branch. So where it is located on the second carbon. Since it's located on the second carbon, we are going to call it 2-methyl. So we have completed the name of the compound, and we call it 2-methyl-1-propanol. All right, and that's the name. Or we can say 2-methyl-propan-1-ol. Okay. All right, so now we have understood, or we come to the understanding as why these compounds have this name. So the first compound is called butan-1-ol because we have 4 carbons in it. This OH group is found on the first carbon, so we call it butan-1-ol. The second one, which is called butan-2-ol. Butan-2-ol, why? Because we have 4 carbons in the chain. And in addition to that, we call it 2-ol because the OH group is found on the second carbon. Why is that? Because we know that when we are numbering the carbon chains, we number them based on the carbon that is closest to the functional group. All right? So we begin by getting the functional group to the lowest possible number as that is possible. All right? So in this case, we're going to call it butan-2-ol. The next one, we call it 2-methyl-propanol. Why? Because, one, we need to find the longest chain first. The longest chain is 3 carbons, so that's where we have propanol. All right? The alcohol group, or the OH group, is found on the first carbon. That is where we have the 1 here is found on the first carbon, and the methyl group is found on the second carbon. So that's why we have 2-methyl-propan-1-ol. And lastly, we also have this example here, which we could have also put into K, where, one, you need to find the longest chain, and in finding the longest chain, this is the longest chain that we have here, we number the carbons based on the lowest possible number given to the functional group, and therefore we are going to have propan-2-ol, where the 2 says the OH group is found on the second carbon, and then we have 2-methyl because the methyl group, which is the branch that we have here, is found on the second carbon.